All right, welcome to lecture. We'll get started here in just a second. We're off to chapter 11, which is kinetics. And again, the notes should be up online if you need them. So again, for those coming in, we're off to chapter 11. Again, the notes should be up there online if you need them. And we'll get started in just a second. Like usual, if you do have any questions, feel free to ask them in the chat box. Again, we'll get to your questions if you do have them, and just type them in there, even if we've sort of moved past it. And we'll get started here with chapter 11 in just a second. And again, like I said, these notes can be found online if you need them in the module section. All right, so we're going to start here, chapter 11, which is the final chapter of the season here. So we're down to our last one here in our last couple of weeks together. So we're going to finish up talking about chemical kinetics. It's also the basis, I think, of the last lab that we'll have is the kinetics lab, which will be up shortly, I think. I don't know if we're going to do very much out of it, but we will maybe do a part of it, I think. It's all they kind of filmed. So that might be all that we'll do. So kinetics definitely is important. I would also say that this chapter's going to be kind of important for you as well next semester if you continue on, or whenever you continue on to take, what are we at there, 200B that comes after this class. So although it's not typically sort of discussed in 200B, unless things have changed, which I don't think they have very much, the final in 200B will cover kinetics as well. So you used to take, I think, unless something has changed, but you take like the ACS standardized final and a good amount of questions on the final for 200B, for example. Next class that you take does involve kinetics. So you may not want to toss your notes on this one. You may want to hang on to them at least for the next semester as well. If you're off to 200B after this, you'll definitely probably see kinetics again. Again, not formally probably taught to you in 200B, but the final, which again is usually a standardized sort of final, it usually has a good number of sort of kinetics questions on it. All right, so let's get into kinetics then. And a couple of things about sort of kinetics and some other sort of properties. So there's really sort of two things that you talk about, and really a lot of these two things are sort of discussed now in 200B. But the idea of thermodynamics, and thermodynamics a lot of times will deal with the idea of whether or not a reaction will actually take place. So when we talk about sort of thermodynamic type properties, the first law of thermodynamics, for example, is the law of conservation of energy, which years ago they used to teach all energy stuff in this class. But again, they moved it to 200B. So in 200B, you'll learn about energy. You'll go back to, I think it's chapter 6, which is the energy chapter. And then you'll also learn about some other aspects of thermodynamics, things like entropy, things like Gibbs free energy, and those type of things. But really what a lot of sort of thermodynamics sort of focuses in on is a basic idea of whether or not a reaction is sort of spontaneous. And when we say a reaction, for example, is spontaneous, it doesn't necessarily mean that the reaction happens super fast. It doesn't mean that it happens super slow or anything like that. It just means really if a reaction is spontaneous under those conditions that you're sort of looking at, what it means is that you would expect that reaction basically to take place. And again, it could be a very fast reaction, could be a super slow reaction. But again, spontaneity really has nothing to do with how fast or slow a reaction basically takes place. And sort of the area of study that does, though, deal with how fast or slow a reaction takes place is kinetics. And kinetics deals with that idea of, again, how fast, or I guess how slow, a reaction will basically proceed. So what we're going to be kind of looking at in this chapter is kinetics, and again, how fast or how slow a reaction will take place, not whether or not a reaction will take place, which again is more thermodynamics, will it take place. So oftentimes what we focus in on when we talk about sort of kinetics is the idea of reaction rates. And a rate is basically how fast something is changing over a period of time. And typically what we deal with is concentrations. And as we talked about, the most common sort of unit of concentration is molarity. So oftentimes when we talk about reaction rates, we end up with these units here, which is molarity over seconds. And basically what we're looking at is the change in concentration over time, which is basically what a rate is, right? How something is changing over a period of time. And if we have a reaction such as the generic one that's written there, A going to B, over this reaction, we would expect a couple things to sort of occur. Since it is a one-way reaction or one-way street arrows basically just pointed in one direction, we would expect this reaction to proceed from left to right, which basically means we would expect it to go from reactants to products. And what that means is over time, what we would expect to happen in terms of the concentration of A in this example would be we would expect it to decrease. And we would expect it to decrease because in order to make our product, which is B, we pretty much need to use up A. So the amount of A we would expect over a period of time to decrease, while in this particular reaction, the amount of B we would expect basically to increase with time. And we can write what is sometimes referred to as a rate expression to sort of illustrate this sort of aspect of what's happening. And that's what we see here. This is the rate is equal to minus the change in the concentration of A over the change in time. So this is the change in concentration as it says down there. And change in concentration is pretty much, final concentration minus initial concentration. And delta T is the change in time. So again, that's your sort of final time minus your initial time. Now, because this is a reactant and we would expect the concentration of this guy to decrease with time, that is also why in this we actually do see the negative here. So this negative that's incorporated into this rate expression deals with the idea that over time, our reactant here is basically decreasing in terms of its concentration. And again, if you just kind of put the units into here, concentration, again, going to be molarity. Time is probably going to be seconds. So again, we end up with that molarity over seconds, which is basically what the rate is. Now, it's a little bit different when we talk about the product side. On the product side, we would expect as this reaction is basically proceeding, we would expect more products to be made, and we would expect an increase in the concentration of B over time. And we get the same sort of rate expression. The rate equals the change in concentration of B over the change in time. The difference, though, is in here. There is no negative. And again, is thought of as being more positive. And we should have a increase in the concentration of B over time. Now, when we basically calculate the rate for this guy and the rate for that guy would be the same since it's the same reaction. And typically when we calculate the rate, we usually get a positive number when you calculate the rate. And that is because of the negative sign that we actually see there. So for example, if we sort of looked at A, go into B, let's just say it started at 4 molar, we would expect it to decrease. So it would end perhaps at 2 molar. While B here would start at 0 and maybe end at 3 molar, right? And if we just see the change part of it, so for example, we take the rate is equal to minus the change in A over the change in time. When we would do our change in A, it's our final, which is 2 minus 4 over whatever the time may be. We'll just call it 10 seconds. But here, when we do this, this negative and that negative will turn our rate into a positive number. And that is typically when you calculate the average rate for a reaction, it should end up being actually a positive number because of that. And that's different than our product. For example, here, if we did it for our B, this is also, again, why there is no negative there. Our final would be 3 minus 0 over, again, I'll just make up 10 seconds. And again, that's going to give us also a positive rate. So when we're displaying how a concentration is changing in molarity per second, you can have a negative or a positive value. But if you're asked to basically calculate the overall rate for a particular reaction, that typically will be a positive value. Any questions on that there? So as you can see here, and especially in the kinetics chapter, a lot of times there's graphs, there's tables that we come across. But here you can see A going to B, again, at the time 0 on the far left-hand side. If A are these black circles here, we have pretty much 100% black circles. And if B are red circles, as this reaction starts to proceed, we start to see the appearance of red circles starting to be made. And you can see, obviously, the red circles, again, would indicate our product being made. And as you continue all the way down to the right-hand side, we see a tremendous amount of red circles versus the black circles. And again, that would indicate that obviously we have made a lot of product in this particular reaction. Again, graphically, that's what we see as well. When we look at this graph, at the start time 0, we pretty much have all reactants, which is represented by this black line. And we have pretty much none of the products there at time 0, represented by the red line. But again, in order to make our products, we have to use up some of our A, which is our reactant. So we start to see a decrease in the A's line, while we also see a increase in B's line to indicate that we are making some products. And this reaction is essentially heading, again, in this direction here, going from left to right. So how do we follow sort of a excuse me, a change in sort of the concentration over time? So there's many sort of different ways that you can follow how something is changing over a period of time. A very common way would be using some type of spectrometry, like a spec 20 or something like that Kool-Aid experiment. And we could follow basically the change in the concentration of a reactant over time based on its absorbance. So if you remember that Kool-Aid experiment, somebody was in charge of figuring out the maximum wavelength. And when you use one of those guys, you always want to set the wavelength to the maximum absorbance for your samples. And what that allows you to do is pretty much take absorbance readings without falling off the scale. So again, if you really should have set the absorbance, the wavelength to here, but you decided to set it way over here, when you would run all your samples, as you can see, you're probably going to be off the scale with most of them. They're not going to be able to be read in terms of absorbance values. When we usually do absorbance or something like that, that is using what is referred to as Beer's law, which is A is equal to BC. A is absorbance. B is sometimes referred to as Beer's constant. And that basically is made up of two things, is that molar absorptivity and the path length, which are sometimes comboed into Beer's law. I think in the Kool-Aid experiment, they split it up. And C is the concentration. So using sort of Beer's law relationship, it allows us to follow what's happening in a reaction by obviously using the color of the solution to our benefit. The way it works, right, when you do any type of spec is basically you have a light source at a particular wavelength, you shine that light through your sample, and it either measures one of two things. It either measures absorbance, which is how much of the light is basically being absorbed by the sample, or it may measure transmittance, which is basically the ratio of light going in to how much light goes out. Remember that absorbance is really based on sort of the color of the solution. So much like in that Kool-Aid experiment, the darker the solution, the higher the absorbance value you should have, while the lighter the solution, the lower the absorbance value it should be. And that is beneficial because we can relate, as it shows there on the bottom, that the change in the concentration of Br2 in this case, and the Br2 is really in this case sort of what is providing that color that we see. Everything else in that reaction is pretty much colorless. So by looking at really the disappearance of that color over time, we can basically figure out what's happening with the Br2. So the Br2 is proportional to the change in absorbance values. And that is basically what this means right here. It's proportional to the change in absorbance values. And that means that at the start of the experiment here, when we mainly have reactants, as you can see, you have that kind of darker orangey reddish color. As your reaction starts to proceed, you're going to make more products. And these guys are on the colorless sort of spectrum, if you will. So obviously what you would typically see in this thing is you would see in this reaction a high absorbance to begin with. And as your reaction proceeds, it makes more products and you get more of the colorless guys in there, you will see the absorbance values start to decrease. And again, you could use something like a Beer's law plot and Beer's law to translate absorbance into concentration. And again, the higher the absorbance, that should mean we have a larger concentration of Br2 in this example. And then obviously as the absorbance values decrease, we would have a lower absorbance value and a lower concentration Br2. And just by sort of analogy of that, you can translate that to mean that you have made more products at that point. And since we're talking about sort of the absorbance and all that good stuff, one other reminder about absorbance, right, and sort of wavelength that we've talked about before. Remember that what we actually see in terms of color is the complementary color to the wavelength being absorbed. And that's why, for example, when we saw the Kool-Aid color of red or something like this, we wouldn't actually set the wavelength of the machine to red wavelength in terms of nanometers. We would most likely set it to the complementary color to red and the wavelength that's associated with that. So that brings up a couple of different things that we sometimes talk about when we talk about rates. And one is what is referred to as the average rate, and one is what is referred to basically as the instantaneous rate. So the average rate is usually over sort of the whole period of time for the reaction. And again, you could calculate that, for example, in this reaction here, since Br2 is a reactant, that's why, again, we see our negative here, a change in concentration of Br2 over the change in time. So really our final minus our initial. And again, because this is a reactant, our final concentration of Br2 will be less than our initial concentration, and we will get a negative and a negative again, as I mentioned earlier, giving us a positive value here for our average rate. And that's different than, say, an instantaneous rate. An instantaneous rate is the rate for a specific period in time. And you can sometimes figure that out by taking, as you can see in the graph, the slope of the tangent of that line, and you'll get an instantaneous rate for a specific period of time. So you can kind of think about it like when you're driving, for example, say you drove from here to Arizona, and, you know, along the way, maybe you average 70 miles an hour all the way there. But different periods of time, if you sort of took your rate as you were driving, maybe you did 75, maybe you're doing 85, maybe you're a very slow driver and you did 55 for a period of time, you know. So for a specific period of time, an instantaneous sort of snapshot of, you know, how you were driving, perhaps you were only traveling at, say, 75 miles an hour. But for the overall average of your entire trip, for example, from beginning to end, maybe again you average about 70 miles an hour and stuff like that. So an instantaneous rate is sort of, again, for sort of a snapshot, if you will, period of time in a reaction as to what's happening. And again, the average rate is sort of you taking the entire reaction as a whole and figuring out how the reaction is changing. And again, you can do that sort of instantaneous rate by taking the slope of the tangent there. It sounds very mathematical, so let's leave it at that. So here's sort of a table of values in a sort of kinetics experiment involving that reaction that we just saw. And when we look at this table, we see a couple of things. What we see is the rate there is, changing depending on sort of the period of time we're talking about. So you can see the rate from 0 to 50 seconds is different than, for example, the rate you got from like 0 to 100 and so forth. But there is a relationship that occurs that is sort of a constant relationship for a reaction at a specific temperature. And that is what is referred to as the rate constant. And the rate constant is that K here. And the rate constant is actually a lowercase k. And I'll just do it for dramatic purposes, not to be confused with capital K. Capital K is what is known as the equilibrium constant. And that also is pretty much all of 200B, what you deal with. But little k, we'll call it, is the rate constant. And the rate constant is basically a constant relationship for a particular reaction at a particular temperature as to how it is basically proceeding. At any sort of given point in that reaction, it will pretty much be a constant value. And as you can see there in that table, pretty much in this reaction, it's a constant value of 3.5 times 10 to the minus 3 reciprocal seconds. And as we'll see in this chapter, the rate constant does actually give us a lot of information about the reaction, kind of tells us how the reaction is sort of changing over time. But it'll also tell us what type of reaction is sort of happening in terms of kinetics. And we'll talk about that a little bit later on this chapter. It'll let us know, is it sort of a first order reaction, a second order reaction, a zero order reaction? And again, we'll talk about that just simply by the units that you see associated with the rate constant. So for example, sort of a preview here, when you have a rate constant that has reciprocal seconds, that indicates that this is a first order reaction. And typically in a first order reaction, the rate's really dependent on sort of one reactant only. So sometimes it could be a decomposition reaction, it could be a reaction that has multiple reactants, but the other ones really aren't participating in the rate of that particular reaction. And if you graph over here, for example, the rate versus the concentration of Br2, we see this sort of linear relationship. And excuse me, where the slope of that line would equal basically the rate constant. Now, as I mentioned, and as we were looking at, sometimes a very easy way to sort of perform kinetics experiment is when you have something that creates a sort of solution that has color in it. And again, that color is going to allow you to do some type of absorbance values because of the color. Again, the darker the color, the higher the absorbance. And again, obviously, the lighter the color, the lower the absorbance values. But again, not all reactions will involve a colored sort of solution, either a reactant or product. And some of them are colorless. So for example, if we did this reaction here that's on the screen, you pretty much are not going to get any type of color in the solution or in a solution. And that's obviously not going to be very helpful if you want to use something like the spectrophotometry to basically figure out absorbance values. Because everything's going to be colorless, you're essentially just going to get zero absorbance for everybody, which obviously is not very helpful. But another thing that you could do to sort of help you still basically follow what's happening in terms of the concentration is actually in this particular reaction, we're generating a gas. And because we're generating a gas, that can bring us really to the ideal gas law. And the ideal gas law is obviously, as we've talked about, deals with a gas, and you can use it to figure out pressure, temperature, volume, etc. We also saw along the way that if you take the ideal gas law and you solve for N over V, that would equal P over RT. And if you take the units of N over V, N is moles and V is liters in the ideal gas law, and that's moles per liter, which is the molarity, right? So you actually can use the ideal gas law and really use it to figure out the molarity of a gas. And if you just think about what you need to monitor, is you pretty much just need to monitor these things. You need to monitor the temperature, which is fairly easy to do, and you need to monitor basically the change in the pressure. So by monitoring the change in the pressure and the temperature, that will allow you basically to figure out how the molarity of something is changing. In this example here, that'll allow you to figure out how the molarity of O2 is basically changing by following those two things. And obviously, if you do this over a period of time, you could get basically just from the pressure information, really, the change in pressure over the change in time. And again, insert in our other stuff here will allow you to basically, in this particular example, figure out how the concentration of O2 over time is changing, again, by simply just following the change in pressure and using that ideal gas law. In this case, we would expect, obviously, an increase in the amount of O2 as this reaction is progressing, and that would be obviously accompanied by an increase in pressure. So since the only gas in this entire reaction is the O2, we would definitely expect an increase in the pressure to be associated with O2 being manufactured. And if O2 is being manufactured, then we do know that this reaction is definitely proceeding from reactants to product. Any questions on that there? So again, there's a couple of different ways, sort of practically speaking, if you're doing kinetics experiments, that you can do it. Again, very common ones, especially when there's some type of color involved, that you could follow sort of the absorbance values and related to concentration. It's a very sort of common technique. But again, even if there's perhaps no colors involved, but some type of gas, either a reactant or a product, you can follow the pressure and sort of the change in pressure over time, and also related to how the concentration of that gas is changing. All right. Hang on here. Let's try that again. Okay. I thought we were done with the lecture. That wasn't too bad. All right. There's the rest of it. All right. So this brings us up to what is sometimes again referred to as a rate expression. And a rate expression basically relates how both the reactants and products are changing over the course of a reaction. But of course, whenever we're dealing with any type of reaction in chemistry, it's always important to know how things are reacting. And we always have to take into account the stoichiometry that's involved, right? And the stoichiometry here, again, is still the mole to mole relationship. And you do need to take that into account in a sort of kinetic sort of calculation or a rate expression. Again, because things aren't always reacting in a one-to-one relationship. So it's not always equal sort of reaction that's occurring. Depending on sort of the coefficients there, you may have something in a sort of 1 to 2 mole relationship, a 2 to 3 mole relationship, whatever it may be. So we can write a rate expression for this sort of made up reaction here, where we actually do take the coefficient into account. And it's going to work the same way here as earlier we were talking about. A, which is a reactant, will be the rate is equal to minus, because it is a reactant, 1 over the coefficient. So this is 1 over the coefficient. And again, the 2 is from there, times the change in concentration of A over the change in time. By taking that 1 over the coefficient, that's going to, in sort of one move, if you will, take care of the mole-to-mole relationship that you may be concerned with. We will also do that on our product side. Is the rate is equal to, again, no negative here because it's a product. And also not written here is the coefficient is 1, which means 1 over 1 is 1. And that's why, again, it's not included here, times the change in concentration of B over the change in time. Now, in general, if we write the rate expression for this reaction here, again, we see our reactants are A and B. They both have our negatives. And it's the negative 1 over the coefficient for A times the change in concentration of A over change in time, minus 1 over B, the coefficient for B, times the change in concentration of B over change in time, 1 over C, which is our coefficient of C, times the change in concentration of C over time. And I'm not sure where it went, but 1 over D times the change in concentration of D over the change in time here for our products. Again, both C and D, which are our products, we would expect to be increasing with time, and thus we don't have the negatives associated with it. Now, why this is sort of important is pretty much what this allows you to do is, if you know pretty much just one piece of information, be it how B is changing with time, you can figure out how A is changing with time. You can figure out how C is changing with time, how D is changing with time, and you can figure out the overall rate for that particular reaction. Again, here, if you are going to calculate the average rate, this should be a positive number when you're done with it. But if you're doing sort of how A is changing over time or B is changing over time, you will end up with sort of a negative value in terms of that. Okay, so let's take a look at some here. So why don't you take a second, why don't you write the rate expression for the following reaction and see what you come up with. So take a minute and then we'll talk about it. So just write the rate expression for this reaction. All right, so let's take a look here. So the rate here for this reaction would equal minus 1 over 1. So you don't actually need it there for the CH4. The change in the concentration of CH4 over time. So it would be the change in the concentration of CH4 over time. And again, a reminder that the brackets mean concentration. And usually what we're talking about is molarity here, moles per liter. And that would equal our second reactant, which is -1/2 for the coefficient here, the change in the concentration of O2 over the change in time. And that equals our product, which again is a coefficient of 1. So this would be the change in concentration of CO2 over the change in time. And our final product there, which would be 1/2 change in concentration of H2O over time. So again, in this particular reaction, if you just knew information about one thing, you pretty much could figure out how everybody in this reaction is changing. And again, using the 1 over the coefficients there is going to help you get the right mole to mole relationship. In reality, as we'll maybe see, if you want, you can do just a regular sort of mole to mole relationship and then kind of do the kinetics part, but sometimes it's easier just to kind of do it all together. So why don't we try one where there's actually numbers? So for this reaction, the I minus changes from 1 molar to 0.868 molar in the first 10 seconds. Calculate the average rate in the first 10 seconds and calculate how the change in the concentration of H plus over seconds is basically changing, or not really seconds, this should actually be change in time. All right, so take a minute or two and actually calculate this here. You should get some numbers and see what you come up with. Again, use your rate expression and the actual numbers, and we'll talk about it in a minute or two. Okay, so let's take a look at this one here. So for this reaction, we have I minus, and I minus is initially at 1 molar. It then goes to its sort of final as 0.868. And we're doing this basically in 10 seconds. So we're looking for H plus, we're also looking for the rate, and we're looking for I minus, since that's the information we got. So just from the equation, we could see that the rate is equal to minus 1 over 3, the change in the concentration of I minus over the change in time. Again, here, coefficient is 3. I minus is a reactant, which is why we have the negative. And if we do this and put it in here, we have negative 1 over 3. Now, our change in concentration, our final is 0.868. Our initial is 1. And our final time is 10 seconds and 0, probably. And if we do that, again, the importance of the final minus initial here for our concentration is that's going to give us a negative number. And that will get us positive, in this case, 0.0044. Units here are molarity over seconds. And this positive number would equal our rate, which is the average rate that we're looking for there in part 1. Any questions on that? But now we're also interested in how our H plus concentration is changing with time. So we can find that relationship, that the rate equals minus 1 over 2, the change in the concentration of H plus over the change in time. Now, in this particular case, we're actually looking to solve for this part of it. If I get it, there it is. Which means we already know the rate from above, which is this number. That means that 0.0044 molarity seconds equals minus 1 over 2, the change in the concentration of H plus over the change in time. So again, we're looking to isolate this by itself, which means we need to multiply the 2 to the other side. But it's not just the 2 here, it is also the negative that needs to go to the other side as well. And when you do that, you will end up with that the change in the concentration of H plus over the change in time will equal minus 0.0088. Units here are still molarity over seconds. Now, that also does make sense because, again, if we look at the equation, the H plus is a reactant. So we would expect it to decrease with time. And thus, we have the negative associated with how the H plus concentration is changing over time. Any questions on that calculation, where any of the numbers came from? Anything like that? Okay, so again, if you do have questions, please feel free to ask them. I think we might have another example. So we do, I think. Great. That is the same, I think. Yep. All right, so why don't you give this one a go and see what you come up with. If we take 2.4 times 10 to the 2 grams of NOBr, the molar mass from the periodic table is 109.91 grams per mole. I'll put the per mole here. And if it decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes, what is the average rate of Br2 production in molarity per second? So take a couple minutes here and see what you come up with. So in this case, we're looking for how much Br2 we're producing in molarity per second. So we're basically looking for the change in the concentration of Br2 over the change in time. Okay, so let's take a look here. So we have information about NOBR, so we could write our expression for that guy. So the rate would equal minus 1 over 2. The change in concentration of NOBR over time. And in this particular case, it tells us that it's going to take 2.4 times 10 to the 2 grams. It's going to decompose in basically a 200 milliliter flask. So if we want basically our change in molarity, which is moles per liter, we're going to have to convert our grams into moles. So 2.4 times 10 to the 2 grams using the molar mass that was provided to us from the periodic table. That will get us 2.18 moles of NOBR. We have 200 milliliters, which is the same as 0.2 liters. So if we take that and divide that by 0.2 liters, that is going to get us 10.92 in terms of our concentration. Now, we also want to change in time, and we're looking at time in terms of seconds. So here we have the minutes, so we might want to do a conversion there. A minute is 60 seconds. So that's going to give us 300 seconds there. And now we have everything to put into our rate. So our rate would equal minus 1 over 2, 10.92 molar divided by 300 seconds. Now, an important aspect of this, which is not really sort of spelled out here in this particular problem, is the idea that we see that NOBR is a reactant. And since NOBR is a reactant, as we've been talking about, we would expect the concentration of it to actually be decreasing, which we would expect that really what we have here is a negative 10.92 and a negative 10.92. Because again, when we would take the change in concentration of NOBR, our concentration of NOBR final would be less than our initial concentration of it. And that's going to give us that negative number, which again wasn't really spelled out, but that's how we actually get rid of the negative here in this particular problem. So we take 10.92 divided by 300 divided by 2 gets us a rate for this reaction of 0.0182, again, molarity over seconds. But again, we're looking at BR2, so we want to figure out what is that relationship. And from the equation, we see that the rate is equal to the change in concentration of BR2 over the change in time. Coefficient here is a 1, which is why we have nothing like 1 over 1, basically. It's also a product, which means it should be positive. And what that essentially means is that equals 0.0182 molarity over seconds would be our answer. Because this does equal the rate, we just calculated the rate, and we would get that as our answer here for the concentration of BR2 that's being produced over time. So we're basically making 0.0182 molarity of it every second. Any questions on rate expressions, how to use it to do these calculations? I would say most people sort of screw up on sort of this aspect of it. They sometimes will mess up on, should I multiply by the 2 to the other side? Do I divide by the 2? Do I still have to divide by the 2 when I have the numbers on the right-hand side? So a lot of errors very commonly are made sort of with that sort of stoichiometry part, the 1 over the coefficient, and sort of distributing it correctly when you're trying to find an answer. And also negatives and positives is a very common sort of mistake that people make. Any questions on any of that there? All right, so let's talk then about some factors that affect the reaction rate. And again, these are things that can affect how fast or slow a reaction will take place. The nature of the reactants, meaning sort of what kind of reactant molecules, what physical condition they're in. So typically, smaller molecules will tend to react a lot faster than larger ones. Gases also react faster than liquids, and liquids will react faster than solids. And that's just, if you just think about it, gases are pretty much moving around, flying around, moving, completely broken apart from one another. They're in constant motion. They have a lot of energy, which means they're going to come in contact with other things very quickly and tend to react very fast. Liquids as well have a lot more energy than, say, solids. They also have a lot more fluidity, right? They're able to move a little bit more than something in the solid state, which again would allow it to react a little bit faster. Powdered powdered solids are more reactive than block solids. Again, sort of a larger surface area for reactions to start. Some metals are more reactive than others. So like the activity series of metals, like in those single replacement type reactions, remember that some reactions don't take place, but some will, and they will take place when something is more reactive than another. Just for a quick reminder, right, we talked about the halogens way back when, group 7 there on the periodic table, and reactivity increases as you go up, right? That group there in 7, fluorine being more reactive than chlorine, chlorine more reactive than bromine, and iodine more less reactive than all of those guys. Now, when we have ions, they also tend to react faster than molecules, and that's because ions have pretty much have gone for a swim. They're completely broken apart. They are essentially good to go in terms of reacting because they're floating around free, sort of in the solution, surrounded by water, but essentially free. A very major sort of effect on the rate of a reaction is the temperature. So when we increase the temperature, typically speaking, the reaction will proceed faster. Just logically thinking about it, when you increase the temperature, everybody has more energy. More energy, people start moving around a lot faster. People come in contact with each other a lot quicker, and usually will result in a reaction occurring faster. Vice versa, if you do the opposite and sort of lower the temperature, decrease the temperature, like you decide to take your test tubes or your beakers, whatever you're doing the reaction in, and decide to just throw it on ice. If you toss it on ice, it will typically slow down the reaction for the opposite reason. For example, when you do that, you're basically removing heat and energy. And that removal of the heat and energy is going to ultimately have everybody have less energy and be able to react more efficiently. So as you can see there, typically speaking, if you raise the temperature about 10 degrees Celsius, that usually will result in the reaction doubling in terms of its reaction rate. Not 100%, but it will usually result in that. There's actually a relationship, as we will see in this chapter, between temperature and reaction rate and sort of the effect that it has on it. And that's what's known as the Arrhenius equation, which we'll see a little bit later as well. Another sort of important type of substance that can affect the speed of a reaction is a catalyst. And a catalyst is, again, something that is not a reactant. So a catalyst is not a reactant. It's not a product. And it actually does not get used up in a reaction. So it's there when the reaction's over, just like it was sort of when it began. But really what a catalyst does is it is able to basically, without being consumed itself, basically facilitate a reaction to occur faster. And that's usually what we're talking about when we talk about catalysts. Usually we're talking about a reaction occurring faster as a result of a catalyst being added to a reaction. And those are usually what most people are talking about in terms of catalysts. They're sometimes referred to as a positive catalyst. There actually are catalysts that you can add to a reaction to actually slow it down. And those are sometimes referred to as a negative catalyst. But probably 99 times out of 100, if somebody is referring to a catalyst, they're probably referring to it in the idea of it making a reaction faster and sort of speeding up a reaction. As we'll see a little bit later on this chapter as well, there's different types of catalysts. Catalysts can be there in the same phase, which is what is known as a homogeneous catalyst. It can be a heterogeneous catalyst, which means that the catalyst and the reactants, for example, are in different phases. A lot of times in chemical equations, that is what you typically will see written on top of the arrow. So for example, platinum used as a catalyst. You may even see H plus sort of written there, H plus implying that some type of acid is being used as a catalyst. Concentration also has an effect on how fast or slow a reaction will take place. Generally speaking, the larger the concentration of the reactant molecules, the faster a reaction will take place. And if you just think about what concentration or molarity is, for example, molarity is the moles of the solute divided by the liters of the solution. In order to have a large molarity, that would mean that you have a large amount of solute in there. And when you sort of mix solutions, for example, it is the solute that really is reacting. And if you have a large molarity, you have a large amount of solute, which means there's a pretty good chance that those guys are going to come in contact with each other at a much faster rate than if you had a lower concentration. If you had a lower concentration, that means you would have less moles of solute in there, which means they got to kind of hunt each other down as they're in there, kind of floating around in solution to find each other to react. If we're dealing with something that's gases, the concentration of gases does depend on the partial pressures. The higher the pressure, the higher the concentration of gas. Also, as we've talked about a number of times with gases, the higher the pressure, the higher the, sorry, say that right? The higher the pressure, the lower the volume it typically is, right? As pressure and volume are oftentimes related to each other. So as one goes up, like the pressure, the volume goes down. And if the volume goes down in sort of a gas situation, you drop that volume down. Now you got all those gas molecules in a very small area, which means they are bound to come in contact with each other a lot more times, and thus the reaction probably would kick off a little bit faster than if you had a lower pressure and a larger volume. Gives them more time to fly around before they come in contact with each other, and obviously wouldn't have a slower reaction rate in that case. So we're going to talk about some of these things here, and first we're going to talk really about the rate law. And the rate law expresses a couple of things here. The rate law expresses the relationship of the reaction in terms of the concentration of the reactants raised to some power and the rate constant. So this is sort of a generic rate law that's written for this reaction above. And a couple important things that we see here when you look at it. The first important thing is this is our rate constant, as we talked a little bit about earlier. And again, our rate constant is a constant value for a particular reaction. And it is particular for that reaction, the way it's written, and actually the temperature at which that reaction is taking place. This is our concentration of A to the X order and a concentration of B to the Y order. These are what are referred to as the orders. As you can see, X would be the order for A, Y would be the order for B. You can figure out the overall order of the reaction by adding those together, and that will give you the overall order of the reaction. Now, an important thing that we sort of do not see here in our rate law that we saw in our rate expression is in the rate law, it's all about reactants only. So it is only the reactants that get put into our rate law. Products have nothing to do with the rate law. So that's a really important thing. You do not include products there in a rate law. And the X and the Y, which are the orders, they are actually not the coefficients. So oftentimes people think, oh, it must be the coefficients that I see here. And X and Y are not the coefficients in the balanced equation. Although they may end up being the same number, that is not how you actually get them. They are actually found experimentally. So the orders, the X and the Y, are found experimentally. They sort of describe in terms of the relationship of the concentration of our reactants. If you want to sort of think about it, the order sort of describes sort of the proportion, if you will, that's needed in terms of our reactants to be in that reaction to achieve a certain rate. So for example, say if they were both 1, you need almost a 1-to-1 relationship of A and B in there to get a particular rate to be produced. If it's like a 1-to-2, you need sort of, a 1-to-2 relationship in terms of how much of our reactants in order to achieve a certain rate. So what this means is, since these guys are typically found experimentally and not really the coefficients, you typically will be given in these type of problems a table, and you'll be given a table of information. And in this table, you will be given the concentration of the reactants. You will be also given the initial rate for those guys. And you would use that information basically to determine the orders for the reaction. And once you determine the orders for the reaction, you could determine the rate constant for it. So let's take a look at a table here. And this is a typical table that you would, for example, be given. And you can see in this table, as it goes for the reaction that's on the top there, in this table, we're basically given information about the reactants, the concentrations. We're also given the initial rates of each of those sort of experiments, if you will. So 1, 2, and 3 are sort of like experiment 1, experiment 2, experiment 3. And those are the initial rates that were basically determined. So we can use this table and sort of to figure out the orders of everybody and the rate constant and all that. So when we do this, most people usually will do it sort of mathematically. So sort of take a mathematical approach to do it. You could actually do it if you understand sort of the relationship of how concentration changes to the initial rate. But most people need to do some type of mathematical calculation. So you can use sort of this formula here. For example, the rate 1 equals K times A to the X, B to the Y, for like a generic sort of equation, divided by rate 2 times K to the A and B to the Y. So when we say sort of rate 1 and rate 2, we don't necessarily mean that you go to the table and you choose entry number 1 and you choose entry number 2. What we mean here is you want to go to the table and you basically want to choose 2 entries. It can be any entries in the table, but you want to choose 2 entries where one of the concentrations remains constant while the other concentration varies. And the reason we want to do that is we pretty much want to keep it to really one unknown value at a time. If we pick 2 entries where everybody's changing, we would have way too many unknowns and not be able to solve it. So the first thing we might want to do, example here, is write the generic rate law for this. So the rate for this reaction would equal K times the concentration of F2 to the X times the concentration of ClO2 to the Y. So we're going to pick 2 entries in this table, one where they stay constant, one where they vary. If I take entry number 1 and entry number 2, the concentration of F2 remains constant, while the concentration of ClO2 basically varies. So we could use this equation here to do it. And typically speaking, you usually want to take sort of the larger rate on top. And really the reason to do that is it gets you kind of a pretty whole number usually when you do that. You could do it the opposite and not get a whole number, but sometimes it makes it easier to pick the larger value and put the larger value on top. So I'm going to take experiments here 1 and 2. And I'm going to put number 2 on top and number 1 on the bottom, again, because the rate is larger there. So I'm going to take all the information from entry number 2, which is 4.8 times 10 to the minus 3. And that's going to equal K times the concentration of my first reactant, which is F2, which is 0.1 to the X, times the concentration of my second reactant, which is the ClO2, 0.04 to the Y. So all of that information that I just put there on top, that all came from experiment number 2's entry in the table. I'm now going to do the exact same thing for experiment number 1. The rate is 1.2 times 10 to the minus 3. K, concentration 0.1 to the X, times the concentration of 0.01 to the Y. And again, everything on the bottom came from entry number 1 in the table. And now we're going to do some math. When I divide these two numbers, that is going to give me a 4. When I come over here, the K on top and the K on the bottom, those are the rate constants. And as we talked about, and as the name implies, the rate constant should be a constant value, which means at this particular point in time, I do not know what K is, but I do know that this K and this K should be the same number. So they should cancel out. When I look at what's next, I have X here and X here, which is the order with respect to my F2. And again, for this reaction, although I do not know what X is at this moment, I do know that that X on top and that X on the bottom should be the same number, which means that for this guy and this guy, they will also cancel out as well. That leaves me the last guy there, which is 0.04 on top, 0.01 on the bottom. And when I divide that, I get 4 to the Y. Now, what that allows me to do is now to figure out what Y is. And by the way, if it's not a really pretty number or you can't figure it out, you can take the natural log of both sides and divide. Take the natural log of 4 divided by the natural log of 4, and you'll get your answer. But you probably can figure it out, I'm assuming in this case, Y would equal 1. And in this particular case, that Y would be the order with respect to ClO2. Any questions on that part of the calculation there? Now, once I've done it for one of those guys where I kept it constant, I then want to keep the other reactant constant and vary the first one. So if I look at experiments 1 and 3 here, what I see is the ClO2 is going to remain constant, while the F2 will vary. So I'm going to do the exact same type of calculations for experiments 1 and 3. Same thing here. I'm going to put the larger value on top. So that's going to be experiment 3. That means I have 2.4 times 10 to the minus 3 equals K times the concentration of my F2, which is 0.2 to the X. My ClO2 is 0.01 to the Y. Again, all of that information is from experiment 3. I am now going to put all the information from experiment 1 on the bottom, and that's going to give me 1.2 times 10 to the minus 3, K, 0.1 to the X, 0.01 to the Y. And that's going to set me up kind of a similar sort of calculation. If I divide these two guys here, that's going to give me a 2. Same thing, not sure what K is yet, but it should be the same value. When I divide 0.2 by 0.1, that's going to give me 2 to the X. And this guy will also cancel out. And again, same deal. You could take the natural log of 2 and divide it by the natural log of 2, and you will get 1. Or you could just go X is equal to 1 in this particular case. And that X is equal to 1 would be the order with respect to F2 in this case. And now that I actually have the orders for each of the reactants, I could actually write the completed rate law. And the completed rate law would look something like this, that the rate is equal to K times the concentration of F2 to the first power, which you don't have to write, times the concentration of ClO2 also to the first power, which means you don't have to actually put the 1 in there like usual. We also now know that the overall order of this reaction can be found, and the overall order of this reaction would be 1 plus 1, which is our exponents, and that would be a second order reaction, this reaction. And that comes again from adding both of these together. Any questions on that so far here? And now that we actually do have the orders and we do have the completed rate law, we could actually now determine the actual value of the rate constant. So we could use our completed rate law, which is our rate is equal to K times F2 times ClO2. And if I want to solve for K, K would equal the rate divided by the concentration of F2 times the concentration of ClO2. So you may ask yourself, where do I get those numbers? And the answer is you get them from the table. You could choose entry number 1 if you like. You could choose entry number 2 if you like. You could choose entry number 3 if you like. They all typically should give you the exact same value for K. The only thing that you can't do is you can't mix and match. You can't like take some of the information from 1 and some from 2. You have to use all the information. So if I use the information that's found in experiment number 1, my K would equal the rate, which is 1.2 times 10 to the minus 3 molar seconds, divided by the concentration of F2 in experiment 1, which is 0.1 molar, times the concentration of ClO2, which is 0.01 molar. And if we do the math here, we will get a rate constant of something. We will get a rate constant of 1.2. Now, when we think about units, let's see what cancels. So a molarity here and a molarity here will cancel, and we will actually end up with 1 over molar seconds as our units. And again, sometimes people will write it m to the minus 1, s to the minus 1 as terms of the units as well. And as we'll talk about in this chapter a little bit later, that is actually a good thing because that is the typical units that we see for a second order reaction. 1 over molar seconds is a typical set of units that is associated with the rate constant for that type of reaction. So that's good because this was found to be a second order reaction. Any questions on that? Again, if you use information for experiment 2 and put it in there, if you use the information for experiment 3 and put it in there, you will end up with the same value that we got there. Any questions on that there? So just to kind of summarize what we just saw here, the rate laws are always determined experimentally, which means you will always be given some type of table like that. It may have 3 entries like that table. It may have 4 entries, may have 7 entries, may have a bunch of entries, but you'll be given some type of table of concentrations, initial rates for your reactants. And again, the reaction order and sort of the rate law is always defined in terms of reactant concentration. Again, products are not included in the rate law. And the order of the reactants is not the coefficient in the balance equation. It is found experimentally using that table that's supplied to you. And as we can see here as an example, in the balance equation for ClO2, the coefficient is 2, but the order for that reaction, that reactant is actually 1. So we do see that it does not equal the coefficient. So again, you shouldn't take the coefficient and make it the exponent. You do have to use the table and figure it out, again, experimentally. Any questions on that there? Okay, so we will probably stop here today in terms of lecturing. And let's just talk about what we got left. And that looks like 3 days. It looks like it's what we got left. So a reminder that Thursday, we will not have a live lecture. That will free up the time for you to take your last exam, which is exam 4, I believe. And that will be over those couple of chapters, I think. I think that's 9 and 10, I want to say. So the exam will be available around the start of lecture, about 5:30. Like usual, you go on, do your honesty agreement, do the exam, upload your work. You do need to make sure you upload the work in a timely fashion. I think you'll have 30 minutes to do so, which should be plenty of time. And a reminder that your answer online does need to match your answer that's in your work. And you do need to answer the questions online in order for you to get credit. So we won't have lecture on this Thursday. You'll just take the exam. That will leave us next Tuesday, where we will hopefully finish up the rest of this chapter. And at some point, we'll decide what we're going to do with that last experiment, the kinetics one. We'll do something with it, I think. And then that will leave us next Thursday, or a week from Thursday, which will be our final, which will cover all the chapters. And that will occur, obviously, starting around 5:30 during our normal lecture time. And then that will be it. Yes, it will be summer, and this class will officially be over at that point. Any questions on any of that stuff? A reminder that I did post the colligative properties experiment, and the only thing that you have to do on that is the pre and post lab questions, which I would highly recommend that you do that. And the reason for that is that is part of what's going to be on the exam on Thursday, right? So it's good practice for the exam. That covers that freezing point, boiling point elevation. So no video to watch, no data to fill in terms of experiment 13, I believe it is. You just need to do pre and post lab questions, which should hopefully benefit you from the exam that's going to be on Thursday, which will have obviously some of those type of questions on there. In addition, you should also have out there, I want to say maybe another gas experiment that should be out there, 12, whatever that was. I think it was that. Make sure that those get in as well. And that will, again, only leave us really 13 left to do, and we'll figure out what we'll do on that. Any questions on anything that's happening or anything like that? Okay, so make sure you do study. If you have questions, feel free to contact me. I will open the lab section in about 20 minutes or so. If you are having questions on anything, feel free to come through there. I'll be there for a little bit, and then I'll probably sign off as well. But probably about 7:20, I'll open it up. If you do have questions, feel free to come through the lab link. Other than that, I think that covers everything. Any questions on anything? Okay, so have a good night if you're out. If you do have questions, again, feel free to come by at the beginning of lab. I'll be happy to answer them. Otherwise, I guess we'll see each other live again next week on Tuesday. Again, remember your exam is Thursday on chapters 9 and 10.